So now, and then we discussed about radiation pattern. The radiation pattern, we said that what is radiation pattern? That we define by saying that it is the angular variation of radiation in the far field, not in the near field or not in the reactive near field, radiative near field, not the active region, only in the far field. Then the pattern is maintained. In the far field, everywhere you will get the same pattern, not in the radiative near field. Therefore, remember that it is angular variation of the radiation in the far field. In the far field is important. So in the far field due to the antenna. I showed an example of a directive antenna. First, I have shown you one isotropic antenna. It radiates equally in all directions. In this picture, we saw a radiation in a particular direction, which is preferred direction. There, the radiation is maximum, and there are small amount of radiation in other direction. The direction in which it is maximum, that direction we call the lobe along that direction is called the main lobe, and other lobes in which it is not maximum, those are called minor lobes because there are minor radiation. So they give us radiation direction in which it is being radiated. Then we defined what is elevation plane. Elevation means from the ground or from a plane you are lifting it up. So in this case XY plane, we took the ground plane or horizontal plane, then we lifted it up to the Z axis. Therefore we elevated to the Z axis. So if we measure from Z axis an angle theta towards XY plane, that angle we call the elevation angle, and the plane in the Z axis is called the elevation plane. Similarly, we have the azimuth plane which is in the XY plane. So we had major lobe, minor lobe, elevation plane, then azimuth plane. Then also we had two types of field. We called one field to be the E field, other field to be the H field, and we defined what will be the E field, what will be the H field. That also we defined. Then we started with the side lobes. There is a main lobe. Then adjacent to the main lobe, the minor lobes are called side lobes. That is what we defined. So we have side lobes and main lobes. Between the main lobe and side lobe, there will be null, which means there will be no power. Usually there will be null or there will be minima. There will be minimum. If it is not a null, there can be a minimum. So for the main lobe you have maximum power, then that decreases, goes down to a minimum value which can be 0, then it again increases, comes to a peak value which is less than the maximum power of the main lobe. So then again it goes down to a minimum value. So that forms the side lobe. So the angular separation between the nulls of the main lobe and side lobe, or the nulls between the main lobe of side lobe, is called the so that is called a bandwidth, a beam width. Which type of beam width? Fast null beam width, because they are the fast null or fast minima, of course. So this is the beam width, which is the fast null beam width. Similarly, if we are coming on the main beam from the peak, we come down to a power of half. Half means in the peak, if I have power 1, at this point I have power 1 by 2, half of the power. 1 by 2 power means, how do you find power? P is equal to, or P is proportional to E square. So E square is equal to 1 by 2, E is equal to 1 by root 2, which is equal to 0.0707. So if I am considering power pattern, then it should be 1 by half. If it should be half. If I am considering the field pattern, then it should be 0.707 of the peak value. So if we consider those points, I will have 1 point on the left side of the lobe, 1 point on the right side of the lobe. The angular separation between these 2 points is called the half power beam width, and these points are called the half power points. So we discussed about main beam maximum directions, half power beam width, fastenal beam width, then minor lobes, side lobes, and back lobes. Then we saw that the main beam can be in the end fire direction or in the broadside direction or between them. End fire direction means it is along the normal to the z axis. So if it is along the normal to the z axis, which is the top one, that shows the end fire direction. Broadside is, it is along the z axis, which is the bottom one, and in between is which is the mid one. It can be anything in between end fire and broadside direction. Now these patterns have got different names. A popular name is called pattern of 8, which is, if you look at the end fire direction, if I rotate that by 90 degrees, that will give you a figure of 8. It looks like a 8, so it's a figure of 8. Similarly, if you look at the bottom one, it looks like a fan blade. Therefore, that is called a fan beam. The other one is called a figure of 8. So there are similar designations for different types of power. So antennas are referenced based on these patterns: end fire, broadside, fan beam. So these are different ways of referencing antennas. Then we discussed about the radiated power. We found, or we know that the pointing vector, average pointing vector, is equal to 1/2 E cross H star. From that you can find out power by integrating S over the sphere, spherical surface, complete surface. So it is a surface integral. That gives you P is equal to 1/2 eta. What is eta? Eta is the impedance of the free space, intrinsic impedance. So 1/2 eta, surface integration. S has E and H. H can be related to E in terms of surface integral. So we have related that. Based on that, we have E has two components, E theta, E phi. So it is integration of E theta square plus E phi square, R square d omega. D omega is the solid angle over which we are integrating to find the surface total power. Then we define what is radiation intensity. It is the power radiated in a given direction for unit solid angle. So that we have designated as U theta phi, which is equal to 1/2 real of E cross H star dot R square R cap. Now that first part you know is S theta phi, so S theta phi R square. Accordingly, if we can rewrite that as U theta phi is equal to UM into F theta phi. What is UM? It is the maximum value of U. So maximum value of radiation intensity. What is the maximum value? So you have a theta value along which it is maximum. Go to that theta value, then move in the phi direction, find out the phi value in which it will be maximum. So then find out what is UM at that point. So that gives you the UM value, maximum value of UM. Normalize U with respect to UM, then you can write U theta phi as UM F theta phi square. Then if I want to find out the average, what I have to do is just integrate it over the surface of the sphere and divide it by 1/4 pi, because 4 pi is the angle at the center of the sphere containing the antenna. It is the solid angle. 4 pi is the solid angle. So that is how we defined UAV. That can be as P upon 4 pi. So that we defined. And then we came to directivity, defined it as the ratio of the radiation intensity in the reference direction to the average radiation intensity. Usually we take the reference direction to be the direction of the maximum power or maximum radiation. So accordingly, D can be UM by UAV. So maximum intensity by average intensity is directivity. That is UAV we have found out P upon 4 pi. So accordingly, D is equal to UM upon R divided by P upon 4 pi R, which is equivalent to power density at a distance R from the antenna. So this is another definition for the directivity. So directivity is power density at a distance R from the antenna. Then we define beam solid angle, in which we said that let us take a solid angle which contains all the power radiated by the antenna. So if you can find out a solid angle that contains all the power radiated by the solid by the antenna, that is called the beam solid angle, and numerically we can write it as omega A is equal to surface integration of f theta phi square d omega. F theta phi is the field which is the E field. It is not the power. For power we are writing P. Then from beam solid angle you can find out what is P. So P will be UM into omega A. Then we can use what is U average, then define what is directivity D. D is equal to UM by U average. From that you can find out D is equal to 4 pi by omega A, which is the beam solid angle. So if D is equal to 4 pi by beam solid angle. So this gives the pattern shape or the directivity. The directivity as a function of pattern angle is given as d theta phi is equal to D. D is the maximum value into f theta phi square. So remember that f theta phi, the pattern square, is important in finding UM, U, directivity, whatever we are discussing the pattern. Then we defined gain as 4 pi UM upon PM. As a function of angle, we defined it as G theta phi is equal to F theta phi square. Then radiation efficiency from this we found out, and we defined it as the power radiated by the power given as input. So ER is equal to radiated power by input power, which is equal to P upon T plus P0. P0 is the ohmic losses, P is the power radiated. We assume that there is no other loss. So in this case, 0 will be, or ER will be between 0 and 1. Then once we know ER, then we went back to directivity. Directivity we defined as UM by UAB, that we remember. So from that we found UM by P in by 4 pi into ER. So from that we found D is equal to G by ER, which gives G is equal to D into ER. This is an important relationship. Remember this always. The gain and directivity are same except for the factor of radiation efficiency. Radiation efficiency has no unit, so it is unitless. Multiply that with directivity. So if we know directivity and efficiency, we can find out gain. Then we define what is beam efficiency, what is polarization, then what is Friis formula. These three we define. I am not going to go through it once more. This is available in your notes. So I will not go through it once more. I will skip it. Then we started the real thing, which is the potential, EM potential. We started with divergence of B is equal to 0, and we know that divergence of a curl is equal to 0. So we expressed B as curl of A, and we called A to be a vector potential. Then we use that in curl of E, which is the time derivative of B. For time derivative of B, we used del cross A, curl of A, and ultimately we found out E plus time derivative of A is equal to minus grad phi, where phi is called the scalar potential. So we defined two potentials A and phi, but the problem was for A, we had curl of A is equal to B, but we didn't know what will be divergence of A. So since we didn't know divergence of A, it meant that A is not clearly defined. A can take any variable. Now to look at that, we looked at different conditions. In the process, we found out Lorentz condition. How we found out Lorentz condition? Using a Gauss transformation, we saw that the fields are invariant under Gauss transformation. If we take phi dash as phi minus dou Tf and A dash as A plus grad F, then there is no change in the fields for A and A dash phi dash or phi and A, which means they are not being affected under any transformation. So using that, we found out a condition for A, which is del square A minus 1 upon C square dou T square A minus grad of divergence of A plus 1 by C square dou T phi is equal to minus mu J. This we found out from the expression for curl of B. So in the curl of B, if we put A and phi, we found out this. Now here came the brilliance of Lorentz, who said that the first part is a wave equation, the second part is not a wave equation, but the second part gives us a condition under which divergence of A is related to phi. So he said that let us take this condition as 0. So he put divergence of A plus 1 upon C square dou T phi is equal to 0, from which we found out divergence of A is equal to 1 upon C square dou T phi, which is the Lorentz condition. If we use that, then we get a wave equation. What is the advantage of this? Advantage is, if you look at Maxwell's equation, using both the curl equations and divergence equations, you can get wave equations for E and B or E and H. Here we said that A and phi are defining E and H, which means A and phi must obey the wave equation. Right? Now using Lorentz condition, we saw that it is obeying wave equation. So once we know wave equation, then we moved on to solution of wave equation. For solution of wave equation, we looked at the retarded potential, which we said that if there is a source or if there is a disturbance at t is equal to 0, the disturbance will be felt at a distance r at a time t is equal to r upon c. Therefore, if we are observing at a point r, the disturbance or the effect, then the cause has been at a point r dash. So r dash is the source, r is the observation point, and their relation is through retarded potential or retarded time. The time we have found out, or the relationship between r dash and r, we have found out r dash is equal to So R is equal to R dash R dash is equal to R minus C upon R. Next. Then for solution, we rejected to the method of Laplace transformation and Fourier transformation. What I said is these equations for E and phi are dependent on space and time, which means these are spatio-temporal variation equations. And we know from early mathematics that a differential equation can be easily solved if we take its Laplace transformation or its Fourier transformation. Now, in this case, we have the time domain as well as the spatial domain. So, for the time domain, we took Laplace transformation. For the spatial domain, we took Fourier transformation. So, using that, we simplified our wave equation. Once the wave equations were simplified, which means we brought them down to algebraic equation form, then we solved them. After we solved them, then we solved them in the algebraic form of equation. So after we solved, what we have done now, remember, for the temporal part or for the time part, we used Laplace transformation. For the space part, we used Fourier transformation. So in the Fourier transformation, from the x domain, we went to the kx domain, or from the space domain, we went to the k domain, or the wave vector domain. Right? Now we solve for u. U is representing either phi or a. So then we solve for u. Once we solved for u, found out u, then we took the inverse Laplace transform and inverse Fourier transform, that and that gave us the solution. Now the solutions were of the form for solving u, we used the Green's function and found out in the form that is shown in the above equation. We use that, we use the convolution of Green's function to find out the complete solution. Right. So I hope you don't have any doubt in this place. Reason is simple. It is very simple. Steps are simple. Take Laplace transform for time domain. Take Fourier transform for frequency domain. Solve it. The solution is your Green's function. Now, once you know the Green's function, take the convolution of the Green's function. Why? And you taking convolution will give you the real answer that we'll discuss later. But remember that if you take convolution of a function with another function, you get uxt. So that we have used. Using that, we have found out the solution for potential. So finally, we have inverted for the Green function. We used the Green's function. We used the Green's function and we found out the solutions in this form. Uxt is equal to 1 by 4 pi f of x dash t minus r upon c divided by r or integrated over the whole value. Right? So we are going to use this function in our solution. So u is equal to a or phi and f is equal to minus mu j or minus rho upon epsilon, from which you can find out what is a, what is phi using the previous steps. So this was in time domain. Just to give you a glimpse of or the essence of time domain, I did that. If that is difficult, don't worry about it. Straight away come to the time harmonic form. Before coming to the time harmonic form, we discussed about Hertzian dipole. For the Hertzian dipole, AR will be 1 upon 4 pi integration of mu j e to the power minus j kr by r over the volume. For that, we have defined what is polarization in the medium, which is j pole. Then what is P? P is equal to P delta Q R. J R is equal to J omega P delta Q R. So these are the things that we define. Accordingly, we found out what will be H and E. If we go to the time harmonic case, we consider the time harmonic case for Hertzian dipole, and in the time harmonic case, we found out the fields. And comparing the fields, we saw that there is near field, which is varying as 1 by RQ. There is a field component which is varying as 1 by R square, and there is a component which is varying as 1 by R. 1 by R is the radiation part. So we considered what will the HRAD and what will be the ERAD, found out the expression for HRAD and ERAD, taking only the components which are varying as 1 by R, neglecting the other components as near field, which we considered later. Then we saw that HRAD and ERAD are related by eta 0. Eta 0 HRAD is equal to R cap cross ERAD. So that we saw for Hertzian dipole. Then we looked at their near fields also. Then for the complete expression in the harmonic domain time harmonic field, we define P as e to the power P as P z cap e to the power j omega t. Then we defined G R T. So on that we multiply G multiplied with e to the power j omega t. So from that we obtained different values which are j omega into jk plus 1 upon r. Simply multiply that, that gives the right hand side. Similarly, for the next one, we multiplied that and took the real part. Taking the real part, we got the right hand side. Then in the third one, we took the real part of j omega jk plus 1 upon r g r t. Real omega, okay. So there was a question in this. From where P came, I should have corrected this. This is a mistake on my part. This P comes from the fact that for H and E, we are using P, right? And P is multiplied with G. E and G are multiplied in both H and P. So if I take P common, multiply that with G, then my G will be GRT, and P I can take common as P into GRT. So if I take small p, GRT, that will be equal to whatever I have written for the G into small p, right? So that small p comes into account here. That is how you are getting P. Okay. So that I had excluded in the last part. This part I expected to show that, but I forgot. Then once we do that, we find out what is E and what is H. Once we found out E and H, then we found out, or we used our knowledge of Z cap is equal to R cap cos theta minus theta cap sin theta. Using that, we found out what is R cap dot Z cap, R cap cross Z cap, and R cap cross Z cap cross R cap. we found out the expression for those, put those expressions in E and H, which gave us ER, E theta and H phi. All other components are 0, which means E phi is equal to 0, HR H theta is equal to 0. Now we have got a radial component and we have got a component along theta and phi. So from that, we know the radial component is not contributing to the radiation. Only theta and phi components are contributing to the radiation. Therefore, for confirmation, we used S is equal to 1 by 2 E cross H star. Put the values of E and H. It showed that we get S, or the Poynting vector, to be a real valued vector, and it is directed radially outward, which means radiation is going out radially. There can be a confusion. I want to clarify that confusion at this point. The power is distributed over the surface. So the power or the energy is on the surface, and the surface is expanding as we are expanding or as we are increasing the radius. So you should not confuse with I say that radiation is going out radially. Radially, when I say it is going out radially, means the surface is expanding. Radiation is along the surface. Radiation is not along the radial direction. It is along the surface, but the surface is expanding. If I expand the surface, I am finding out the radiation activity. Right? So going out radially means this. Once we find out S, we know how to find out total power. So PF we found out by integrating S over the surface area. That gave us omega mu k upon 12 pi into P square. Then we saw an animation in which we saw where is the antenna and how it is radiating. In the 3D and 2D, we saw how it is radiating, which means we saw that the current is, or the charge goes to peak positive, which is yellow, then it goes to peak negative, which is blue. But when it goes to peak positive, the fields are forming from positive to negative. When it goes from negative to positive, they are forming from positive to negative in all cases. So, and they are rotating from positive to negative, negative to positive. And in the process, when it is 0, when it is at the center of this peak, you see the peaks are up and down. When they are at the center, there is detachment of the fields. So they are going out from the antenna. This is what we saw in the animation last class. Then we considered the near fields. The general expressions are valid at any distance. Remember this. The general expressions are valid at any distance, which means it contains, the general expression contains radiative field, near field. When we are considering near field, we are considering the field that is dominant. So always remember this. When we are considering far field, we are considering the field that is dominant there. There is near field, there is radiating near field, but they are negligible compared to the dominant field. So we found out expressions for near field, Hn and En. Then we found out the power density. And when we found out the power density, we saw that power density is an imaginary quantity. Since it is imaginary quantity, which means there is no radiation, it is only stored field. There will be no consumption of power. Therefore, we call it reactive near field. Then we looked at how to find out lines of force. We know that E field is tangential to its field lines, Based on that, we said that if we change along E field a distance dr, that will be parallel to the E field. So dr cross E will be equal to 0. So that can be this relationship we used to determine the lines of forces or field length. So what we did is we took the cross product of dr with E, that gave us dr by d theta is equal to r into er by e theta, right? So once it gave us this, we found out that r is related to theta. We found out a relationship between r and theta. Once you know what is the relationship between r and theta, then you can easily plot between r and theta. So take in one axis r, other axis theta, you can easily plot. For plotting, we made some simplification. We defined kr to be r, alpha, omega t to be zeta, and minus E0 as pkq by 4 pi epsilon 0. All these are dimensionless quantities. We use them in the expressions for E, er, E theta we found in this term. Then we found that the bracketed term for E r, if we take its differentiation with respect to alpha, that gives us E theta. So that also we saw. So one that gives us with that knowledge, we defined E theta, E phi as we defined two terms, psi and d psi by d alpha. Both are functions of alpha. Accordingly, er is equal to E0, 2 cos theta by alpha square phi alpha. Similarly, E theta is equal to minus E0, sin theta by alpha psi alpha, which is a function of alpha. Now, the equations for lines became variables of alpha. We use d alpha by d theta as alpha into er upon e theta. So from that, we found out this expression, minus 2 cot theta psi alpha by psi dash alpha. Now, if we look at that, then we can say d upon d theta of log psi alpha is equal to minus 2 cot theta, which is equal to d by d theta of logarithmic of sine square theta. This is simple calculus. So if you remember those, we can easily, you can derive those things. Now that we equated to 0, once we equated that to 0, we found out psi alpha sine square theta is equal to phi constant, which is q. So that constant we can solve. For that constant, ideal method is solve r in terms of theta. This is very difficult to find out a closed form relationship between r and theta, although there is a relationship in terms of their derivative dr by d theta, but closed form relationship does not exist. We found out the alternative method. We thought the lines as contour plot at different values of the constant q. Then we wrote a program for the contour q and saw how we can plot the contours. I gave an outline of the pseudo program, and I expected that you will write the program yourself and see for yourself or enjoy for yourself how lines of forces are being formed.